Now we're going to start talking about the three energy systems and how we use them to create ATP. And the analogy I used in class is all three of our recipes have the same end result or the same end product, but they have different ingredients and different processes and steps that you take to actually build that end product. And each one has different advantages and disadvantages. So if you remember in class, I used the analogy of a match, a newspaper, and firewood as an analogy for the different energy systems. So the first one we're going to talk about is your ATP-Pcr system, which we said was like a match. And what PCR stands for is phosphocreatine. And if you've ever heard of creatine, and we'll get there in a second in this video, we're going to talk about how creatine actually comes into play with this energy system. So what do we know about a match? The first thing we know about a match is that matches don't last very long. And so your ATP-Pcr system is very good immediately for very quick activities. It doesn't take long to light, but it only lasts about 6 to 10 seconds. So your ATP-Pcr system is going to have a very limited duration. However, it can give us energy very quickly. And as I said in class, and I just want to reiterate, remember that this system always initiates activity. So even if it's an hour-long activity you're starting, a 10-second activity, a 4-day activity, whatever it is, that first burst of energy you use when you start an activity, going from rest to activity, is predominantly from this ATP-Pcr system because it gets you a jump start. It starts the fire. Now, in your body, unlike a match, you don't have to grab a new one to actually replenish the system. It will actually replenish itself and will start refixing itself with recovery. And so for your system, if you went all out for 10 seconds, and you completely used all that fuel and you exhausted that system, so you fatigued the system, it would take you 3 to 5 minutes before it was fully back to normal. And when we're thinking about activity, if we're thinking about weightlifting as an example, and we wanted to train this energy system, or if we're working with sprinters who needed to use this energy system, you would want to make sure that you are giving them about 3 to 5 minutes of recovery if you truly want to train the system. Because if you did 10 seconds all out effort and then you only waited 10 seconds, a different energy system is going to have to make up the difference because this one's not yet fully recovered. So this directly ties into our SAID principle. So the SAID principle says specific adaptations to impose demands, right? If I want to make this energy system better, I need the activity to last about 6 to 10 seconds, and I need to give you rest of 3 to 5 minutes if we're going to do back-to-back efforts. And so you need to understand those original principles because that will then explain how we use this system. Now, what is the recipe for your ATP-Pcr system? There are 2 different ways you produce ATP through this system, and they're very short recipes. They're actually one-step recipes. So, like I said, during physical activity, we break this bond. We then use that for muscular contraction. I want you to pretend, and it's not technically accurate, the phosphate group is still in that muscle cell, it doesn't disappear, but for the sake of it, let's say we have ADP, or adenosine diphosphate, and we want to now attach a new phosphate group. All right, so how does your body actually produce this ATP? Now, we have an adenosine diphosphate, or a 2-phosphate group, and we need to add a third one in to create that ATP. You also have creatine phosphate, which is a creatine molecule as well as a phosphate group. So all this process is, and think of it as a 1 or 2-step recipe, is all you do is you break this bond here, and you take this phosphate group up here, and you actually attach it onto the end here. Okay? So then we have a lone creatine group, and then we have adenosine triphosphate because we moved this group up here and then we reattached it. Okay? Now you have ATP, now you can break that bond and produce that energy, and then you're going to repeat this step over and over and over again. So if we're thinking about this system, because it's only 1 or 2 steps, right? You're breaking this bond and you're reattaching it somewhere else, it's not going to take very long, which is why this energy system lasts 6 to 10 seconds, or it's able to produce energy right away, is because it doesn't have a series of steps. When we look at glycolysis, you're going to notice that there are, depending on how you break them down, roughly 10 steps to that process. And so it's going to take much longer because each of those reactions has to happen in sequence. So that's the first way this system creates ATP. Now, the second way this system produces energy is if we're thinking about energy, we're thinking about ATP breaking down. We would have a lot of that going on when we first start an activity, right? Because we haven't ramped up energy production. And so what your body actually has is it has a surplus of adenosine diphosphate, right? Because we've broken off the third one and now these ones are just floating and hanging out. If you remember in class, we talked about why it's more efficient to break the third bond for energy than it is to break these individual bonds. Because there's some energy stored here and there's some energy stored there, but it's nowhere near as much as the amount stored in that third bond. And so what your body actually does is it thinks it's better, or it's a better strategy in terms of efficiency, to break a bond on an adenosine diphosphate. So now we have adenosine monophosphate with just one ATP, and then it takes this third group and it comes up here and it attaches it so you have a new adenosine triphosphate. So it's better to have one adenosine triphosphate and one adenosine monophosphate than to have two adenosine diphosphates, just because of that third bond and producing energy. Now, the next thing we're going to talk about is where these reactions take place. Because if you learn where they take place and how it works, you can actually understand how the system works and how it actually functions. So if we think about a cell, and we're talking about a muscle cell here, right? The first thing we know we have is we have an outside barrier or a cell wall. Okay? That keeps everything inside of the cell in one compact unit, and it keeps everything we don't want in the cell outside. Okay? If you also remember when we talked about these in class, you have your mitochondria, we have a nucleus, right? We have all sorts of things inside of this cell that allows the cell to function and properly. The big things we're going to care about are going to be these mitochondria for energy production. And if you remember back to your basic cell function and cell structures, you remember that the entire cell is flooded with fluid, right? Inside here, everything is floating around because you have cell fluid. In a muscle cell, we call that sarcoplasm. And sarcoplasm is just the fluid inside of the cell. Now, your ATP-Pcr system, all of these reactions are taking place in the fluid itself. Okay? So they don't take place in the mitochondria, which is the powerhouse of the cell. They take place in this fluid. Now, if you've ever taken creatine, or if you know an athlete who takes creatine, one of the things you notice is they actually will gain weight, and they will actually gain a good amount of water weight, because creatine, or this creatine phosphate we talked about a second ago, it's actually stored in the fluid in your cell. And so when you store creatine, you actually also add extra fluid in that cell to fill it up so that you have plenty for these reactions to take place. And so your ATP-Pcr system is taking place in the sarcoplasm, or the fluid surrounding all the different structures inside of your cell. Now, creatine supplementation is effective and it can help you perform better. But if you think about the people who take creatine, a lot of times it's going to be your bodybuilders or power lifters or people who are doing explosive type activities. And the reason for that is because creatine is just essentially adding more fuel for this ATP-Pcr system. So for example, maybe, and this is just an example, but maybe before creatine, you only have 6 seconds worth of this energy. By adding creatine, now you can go up to 7 or 8 seconds, okay? That's how it works, because you're adding extra fuel and essentially you're making your match longer so it can burn for more time. And so creatine can do that. Now, if we think about a aerobic athlete or a marathon runner, they're not gonna benefit as much from creatine because the energy system they're using isn't creatine based. They're gonna be using different types of fuel. And so for them, it actually can potentially hurt their performance because the added creatine, remember it's stored with water, and so it's gonna increase their weight, and it can actually add additional weight that they then have to carry for their entire duration of their race. So you typically don't see creatine supplementation in more of your endurance or aerobic athletes because it's not the energy system that they require.